Okay, I think we can begin. Thank you very much. Good to see such numbers in the hall today. I notice an anti-correlation with the weather, but I don't think that is exactly the reason for this today. So I'd like just to pass on for the formal introduction here too.
Thank you. Okay. Michael Perryman, he did his studies at Cambridge University, where he got a degree in physics and a PhD in radio astronomy. And from there, in 1979 or 80, he went to Estek, Nordwijk, for just 1.5 years of research fellowship, when he then became the project scientist of the just approved Hipparcos project, the first space astrometry instrument in history. He became that, he got to that position in the tender age of 27 or so, 26 perhaps. I got to know Michael 2 years later at my very first Hipparcos working meeting. And the formal task of the project scientist at ESA is to advise ESA on all scientific aspects of a mission. But even at that meeting, I did not experience Michael as an advisor, but as a great leader already then at that young age. And that is what has always been my impression of him, a great leader through the Hipparcos mission, through the Gaia mission. And he kept that position of advisor formally, but leader actually, through the entire development of Hipparcos, from approval through industrial development, through definition of the science program, through launch and operations. And during the operations phase, he had the dual position of project scientist and project manager. And until 1997, when the Hipparcos project was finished and culminated in the Hipparcos catalog. Whilst Hipparcos still was operating on its orbit. And by the way, this time includes these mind-boggling weeks after this completely failed launch of Hipparcos, when that put him on a completely inappropriate and unplanned orbit, when for weeks people under Michael's leadership and with your good nerves were just fighting to keep that thing alive, and then putting it to this great success that it was in the end. But still, while Hipparcos was working, Michael and very few colleagues started off designing and planning and inventing the follow-up mission Gaia in 1992, 1993. We submitted the first proposal to ESA, and after 1997, Michael then became project scientist of Gaia, and also not just advised but conducted this project through all its phases, from the fight for approval to the scientific definition, the technical industrial definition, the procurement, up to the critical design review when he quit the project. And in the 5 years from 2008 to the launch of 2013, when the rest of the consortium had to set up the actual operational scheme and processing system, I dearly missed this leadership, I must say. But at that time, Gaia already was in the bag, was in dry towels, as one says in German. And since then, it has proceeded. Michael has been watching it, among other things, spent a year in Heidelberg writing books, big books, heavy books about astrometry and other things. And yeah, he has been a professor at Leiden University during his most of his Aztec time in the Netherlands. And after his kind of retirement, since 2013, he was Bowden Paczynski visiting professor at Princeton University for a year and has been a adjunct professor in the University College of Dublin since 2013, right? Yeah. Recognition of his decade-long leadership in space astrometry include, now I read, the Gold Medal of the French Astronomical Society, the Academy Medal of the Royal Netherlands Academy of Arts and Sciences, the Tycho Brahe Prize of the European Astronomical Society, and most prominently and most importantly, the 22 Shaw Prize in Astronomy. The Shaw Prize, also being much less known than the Nobel Prize, in fact, is the biggest science prize existing, even bigger than the Nobel Prize. And he shared this 2022 Shaw Prize with Leonard Lindegren, the other decisive guy without whom Gaia would not be. And Eric Höck is the third one. Okay.
Well, thank you first to the organizer, Richard. Thank you to my host, Uli, and thank you to everyone else who in Heidelberg over many years has welcomed me during many visits and some recent extended stays. Thank you very much. It's a really great pleasure. Right, well, we'll see how much of a pleasure this is going to turn out to be in a few moments, I suppose. But it's a real pleasure to be here talking to you today. And I know that since this is the joint astronomy colloquium, there are people who don't know so much about space astrometry, about Hipparcos and about Gaia. So my intention is to give a little bit of a selective view. I'm going to spend the first part of my talk putting it in some kind of historical context to explain where we've come from and where Gaia sits in the historical development of astrometry. I'm not going to say too much about how Hipparcos and Gaia made their measurements, but I'm going to move on and just give some examples of some of the science that's coming out of Gaia today. So critical in terms of background is that if we go back through history, go back a couple of thousand years ago, and the stars appeared to be immovable. And it was really about 300 years ago that Edmund Halley was able to measure positions of some stars with respect to the stars that Hipparcos, the ancient Greek, had measured 2,000 years previously. And he realized that some of these were moving. This was the first evidence that stars were moving through space. The other critical thing to stress in terms of these measurements is that with the Copernican revolution in around the 1600s, the realization that the Earth was moving around the sun, there was an inevitable conclusion for this, and that is that you should be able to measure the distance to the stars through the application of the principle of trigonometric parallax, just the simple geometrical motion of the Earth around the sun, viewing the stars from two different viewing directions would mean that a nearby star should appear to move with respect to the background stars. Now, it took 250 years between the first attempts to determine the parallax of even the nearest stars was successful. That materialized in about the 1830s with Bessel, Struve, and others measuring the first trigonometric parallax, measuring the first displacement of a nearby star with respect to the background stars. And this was at the same time a confirmation of the Copernican principle that the Earth moves around the sun, but it was also a demonstration of the immensity of space. This was the first time that distances had been measured to the stars. And I won't go into too many examples there, but here's one analogy. If you took the world's population of 7 billion people and spaced each of them by 5,000 kilometers, that would get you to the nearest star. So these are really they are unimaginable distances, and the consequences are really unimaginable. But if I now look at our galaxy would look something like this. This is M31, the Andromeda galaxy. Our own galaxy would look something like that if we could see it from the outside. We're sitting out in one of these spiral arms about 30,000 light years, about 8,000 parsecs, 8 kiloparsecs from the center. And the first mission to measure star positions from space, Hipparcos, this was its circle of influence. If you can see there, this little yellow circle, it is broadly the kind of distance out to which Hipparcos was able to measure trigonometric distances to the stars. Comparing that with, of course, what you'd like to do, which is stretching out and measuring distances and motions right throughout the galaxies, is a very big jump was required. And I must say, at the time of Hipparcos, between 1980 and 1997, most of the time we had no real comprehension that it was going to be possible to do significantly more than this. That materialized sort of in the early 1990s with the development of many different types of technology. And the end result of that is that sort of figuratively, Gaia, it reaches out to this kind of distance. So this circle here, or imagine that to be a sphere. It depends on the brightness of the stars, the absolute magnitudes, of course, but this is broadly what Gaia is doing. It's extending our ability to measure distances directly and space motions directly out to the scale sizes of our own galaxy. Now, I'm going to spend 5 minutes giving you a historical run through history, and there's a number of things on this view graph. I'm going to show the accuracies that are achievable, the accuracies compared to some kind of yardsticks that you can comprehend. I'm going to mention a bit the technologies that were used, and I'm going to mention the science that became accessible through these kind of astrometric measurements. So I'm going to start the story with Hipparchos, the ancient Greek, and this is, apart from a jump there around 2,000 years ago, this is a linear scale of time on the horizontal axis and a logarithmic scale of angles. And again, for those of you who are not deeply involved or involved in this field, what we're trying to do is to measure the angular position of a star on the sky compared to other stars on the sky. We're trying to measure angles. That's all we have direct access to. So Hipparchos was measuring about 1,000 stars with an accuracy of about 1,000 arc seconds. This corresponds roughly to the diameter of the full moon. That was the accuracy that was available to him. And I'm just going to jump through and pick out a few selective locations in history. Tycho Brahe, of course, very well known for his positional measurement work in about the turn of the 1600s, measured 1,000 stars, and a big jump in accuracy, getting down to something like 30 arc seconds, the angular resolution of the human eye. The catalogue of Flamsteed, positional measurements became very important because of navigation at sea. The ability to determine your location at sea required the determination of longitude, which required a knowledge of star positions and time. And that is one of the things that really forced the development of improved angular accuracies. I'm going to jump through to the early 1800s and the first large, very, very large scale Durchmusterung, the Bonner-Durchmusterung of I've written 26,000, it might be 260,000. The Cordoba and Cape Durchmusterungs, which were the first of the photographic surveys, measuring something of order 1 million stars. But note that the accuracies that these could get to were about 1 second of arc. So 1 second of arc, it turns out, is the limit, more or less the limit. We can argue a little bit about factors of 10 here and there, but it's more or less the limit that's imposed by the Earth's atmosphere. The Earth is the atmosphere is a phase-perturbing screen which perturbs the positional measurements, and despite best efforts of people over the decades, has been unable to get down to significantly better than that over large angular scales. You can do better than that in very, very small angular regions, but that's the limit of the Earth's atmosphere. And You can see there a sort of logarithmic log linear development over history. And then moving into the modern era, the catalog star positions were very much limited by the atmosphere. And it required the jump to space to take these measurements up above the Earth's atmosphere. So Hipparcos was the first to do this and measured just over 100,000 stars at a level of about a milliarcsecond, 1,000th of an arcsecond. How do you visualize that? Well, an astronaut standing on the moon subtends that kind of angle viewed from the Earth. If that helps you visualize 1,000th of an arcsecond. And Gaia took another enormous leap to bring that down to around 10 microarcseconds. And just to help you visualize that, it's about a Bohr radius at a distance of 1 meter. So it's a very, very tiny angle. Really what you see there is this sort of historical development over 2,000 years. There was this great break in getting to space. And the importance is not only getting above the atmosphere, that's the primary reason to make these observations from space, but there are several things that accompany that. One is the fact that you can get above the gravitational torques, the gravitational influences of a telescope. As you move your telescope around the sky, the telescope sags under different differential gravitational forces, and there are different thermal forces acting on the telescope, which if you imagine trying to get down to a Bohr radius at a distance of 1 meter becomes very, very critical. It's also impossible to measure all over the celestial sphere from one location on the ground, and from space you can do that. You can put together a network of star positions from space. And there are some other important things about going to space, especially the large viewing direction that was exploited by both Hipparcos and Gaia, which I won't try and explain now. But you see that sort of very disruptive motion in where science has taken us in the last 20 years. So just along the top there, just the technologies that were used up until the 1850s or thereabouts. All these observations were limited by the human eye. Then photography, Hipparcos actually used a photomultiplier tube system, and Gaia used CCD, so getting up towards full 100% quantum efficiency, or that sort of order of magnitude. Now, what I would just like to show in brown coming down here is what kind of insights has that given us into the local solar neighborhood or space or whatever. And what you see is that as these angular accuracies, as these star positional measurements have improved, then there has been an accompanying development in our understanding of the galaxy, our solar neighborhood, and so on. So as positions improve, we've got the leading to an understanding of Kepler's laws of planetary motion. Halley in the early 1700s realizing that stars are actually moving through space. A very important discovery, as people were pushing to make these astrometric measurements more accurate, was Bradley's determination of something called aberration. Aberration is the vectorial addition of velocity of light to the vectorial motion of the Earth around the sun. So a star appears to be in a slightly different position because you're adding the Earth's velocity around the sun to the incoming velocity of light. And Bradley in the early 1700s measured this stellar aberration, and it gave a first handle on the velocity of light as well. Herschel, towards the end of the 1700s, realized that he could only explain some of these stellar motions by the fact that the sun itself was moving through space. And in about the mid-1830s, the first measurements of trigonometric distances to the stars. So after a 250-year marathon journey from the initial ideas of Copernicus to actually detecting the first trigonometric parallax was 250 years. What went on for the remaining, say, during the modern era of star positional measurements is a much deeper understanding of stellar evolution. So the characterization of stellar distances. It's only once you can determine a star's distance that you can convert the apparent physical attributes of the star, so the apparent luminosity, the angular diameter, or whatever. You need the physical distance to the star to be able to comprehend the intrinsic luminosity, the linear size, and so on and so on. So distances end up being supremely critical for understanding the stars. Hipparcos really extended this sphere of influence out to, say, of order 100 parsecs. So a first detailed census of the solar neighborhood, the discovery of things like halo stars moving through the solar neighborhood, and so on. And what we see with Gaia, with its 2 billion stars measured down to of order tens of micro-arc seconds, is the first insights, first really deep insights into galactic structure and evolution and formation. And the final thing I wanted to point out at the bottom left there for younger people who have still got their careers in front of them and who find this appealing, this is still accessible. One can continue going down to probably at least 100 nanoarc seconds, or perhaps even 10 nanoarc seconds, before the problems of interstellar scintillation, interplanetary scintillation, and stochastic gravitational wave background starts hitting you. So there's still 1 or 2 orders of magnitude in astrometric positions that would take you out to direct measurements well out into the local group. I'll leave that to younger people who've got. Fascinating question. I don't know. Do we have the commitment to do this? Do we have the societal commitment to do this? Do we have the ability to organize and manage projects that are so huge? And I would also say there's not a clear idea how you would do this. There's not a clear idea how you would get to, say, 100 nanoarc seconds or 10 nanoarc seconds without free-flying optical interferometers. I'm going to touch just very briefly on Hipparcos, 1 or 2 things about Hipparcos. This was the first picture that I could track down from a discussion in the early days of the feasibility of space astrometry. And in the foreground, sitting in the chair at the front, is Pierre Lacroute, who was the originator of the concept of Hipparcos and making astrometric measurements from space. I do want to stress one thing again, why, because we can measure absolute distances to the stars. And this is something that if you take something like Hubble Space Telescope or James Webb Space Telescope, it can make very, very accurate measurements of star positions, but you're measuring a star position with respect to another star nearby on the sky. And if those stars are at the same distance, for example, then their relative parallax will be exactly the same. It's only if you can determine an absolute parallax can you determine the physical distance to the star. And both Hipparcos and Gaia do this by having wide angle measurements. So Hipparcos had 58 degrees between the 2 viewing directions. Gaia is about 100 degrees between the viewing directions. The exact value is not important, but it's the wide angle measurements that give you the access to an absolute parallax. Hipparcos was a very simple optical, I shouldn't have said that, should I? Hipparcos was a very small optical telescope, 30 centimeters in diameter, primary mirror, really stretching technology in terms of manufacture, cutting it, inclining it, gluing it, and a modulating grid, a very, very fine modulating grid, which was necessary to make the modulation measurements of the star as it crossed the focal plane. And that is the flight spare of the beam combining mirror, which sat under my desk in ESTEC for 20 years before I finally persuaded a science museum, in this case the National Maritime Museum in London, to put this amongst their collection. So if you want to see that, it's there in the Greenwich Observatory in London. And this was Hipparcos being integrated in 1987. And what I would like to show you now is some simulations that I made 20 years ago. I haven't seen something similar for Gaia, and they'd be even more complicated. It's enough here to see what's going on. This is a region of about 6 degrees by 4 degrees. It's all the stars in the field of view for Hipparcos. this is the size of the full moon at the bottom right. And in this little animation, all I've done is to put a lateral motion into the stars depending on their parallax. So if they're near to us, they're moving backwards and forwards with a greater amplitude than they are if they're further away. And what you can see from this is the region of the Hyades cluster. You can see that the majority of the stars in the Hyades cluster are all roughly at the same distance. So this oscillation has got a period of 1 year, all right? As the Earth goes around the sun, you're measuring, we're able to measure the distances of these stars. This is enormously magnified, of course. Now, the same is true of the motions of the stars. If I now forget the distances and just show the motions, and I reconstruct that over a period of 60,000 years, what you see is that the stars, of course, are moving through space somehow, projected onto the celestial sphere. You can see that the bulk of the stars are moving left to right. They are the Hyades cluster. You've got one star in the foreground. This is Aldebaran. It's a foreground star, not a member of the cluster. It's moving in a very different way. But you can imagine if we make these measurements at repeated epochs, you can determine the proper motions of the stars. So you've got two things going on. One is the effect of the Earth moving around the sun, giving rise to this parallactic motion. And then you've got the actual star's motion through space, giving rise to this proper motion. So if we add those two together and propagate that over several tens of thousands of years and add the parallactic motion, you can see there that the stars are moving in what appears to be a very complicated way, but in a way that's defined by just 5 numbers: the position, X and Y at some epoch, and the motions of the stars in 2 coordinates, and the parallactic motion. So this is at the heart of both Hipparcos and Gaia. It is measuring at repeated epochs a configuration of stars which is changing endlessly because of the parallactic motion and the proper motion, and a number of other higher order effects, relativistic corrections, orbital binaries, and so on and so on. But you can imagine that by making those measurements, there's enough information then to extract out of that the positions and the distances. So this is a shot of Gaia before launch. You can see some people there in the bottom left for scale. This is the sun shield and solar array is deployed. This was folded up against the satellite during the launch, and hiding in this central black baffled area is the telescope itself, the payload, the heart of the instrument. And you can see it's a massive structure. It's about, what is it, 4 meters or 3.5 meters or so in diameter. The torus is made entirely of silicon carbide, the same as the mirrors. So it's a ceramic, which first of all has a very low thermal coefficient of expansion. The mirrors are made of the same material as the toroidal structure, so that they don't have relative thermal distortions. The ceramic takes a very, very fine polish, so you get extremely good reflective surfaces. And there's one of the primary mirrors, which is about 1.5 meters. It's a rectangular mirror, 1.5 meters by about 0.5 meter in size. There's another one which will be mounted to the top left, and the focal plane in the bottom there. So it's a big system. At the focal plane, a huge area of CCD. So the physical focal plane is about 1 meter in size, with just over 100 large format CCDs. And the telescope is arranged to scan very gently the sky at the same rate as the star images are read out through the CCDs. And at the output of the CCDs, then you read the charged packets associated with each star. You don't need to know the stars that were coming into the field of view. That's all sort of handled through the astrometric sky mappers. And the information then encoding the relative positions of the stars at these epoch measurements are contained in the relationship between the positions of the stars and the focal plane. So just to show that figuratively, there's my region of the Hyades again. There's scan 1, there's scan 2, and the stars have moved slightly. There's scan 3 at several weeks later or several months later. The stars have moved. And the problem on the ground is then to reconstruct that and figure out what are the distances and the motions of the stars. I think at this point, before I move on, well, that's an example of some major. And in fact, I'm going to jump that. But I would just like to point out at the moment that Heidelberg is not only running a very significant and important part of the astrometric solution for the Gaia data. It's head of one of the leader of one of the 9 coordination units that are part of the entire very complex Gaia data processing system. So it's a huge headache. Was Uli, is now Michael Perryman. So Heidelberg is playing a very, very key role in the astrometry, in the positional measurements. And I should add as well that when I first started working on Hipparcos, the institute was under the lead, the Astronometry Relation Institute was under the lead of Walter Fricker. And under Fricker's lead, Heidelberg had been preeminent in positional measurements of stars over something of order half a century, I believe. So Heidelberg has historically been not only a leader in stellar positional work, but continues to do so today through its work on Gaia. Now, I've just picked out one animation so I've given you a sort of historical background. Why is it important? What is it we're trying to measure? And I'm just going to pick out one little animation there, which is just showing the region of space within 200 parsecs of the sun, so about 600 light years of the sun, and a little animation that shows how the stars would move in 1.5 million years. So we're taking a vantage point some way away. Now, what you can see in this animation, without being too didactic or whatever, you can see bunches of stars. There's clusters of stars here moving. There's a high velocity star just whizzed through. These will probably be stars in our halo, which are passing close to the solar neighborhood. But what is key then to the scientific interpretation of the data is something like this star positional motions, how the stars move around the galaxy, how they move up and down in the gravitational field of the galaxy. This is encoding the kind of information we're trying to gather now. I don't know, is that me moving around? Right, should I take it in my hand? All right, let's try that. So this is the kind of information then that's encoded. We've got 2 billion stars, and people interested in a particular problem can go into that database now and look at what that is telling us about the galaxy. Now, the data reduction is a big and complex thing, and so far Gaia is almost 10 years into its measurements. Launched in 2013, full operational phase started in early 2014, so we're nearly 10 years into the mission. It was designed with a 5-year operational lifetime, so already it has exceeded by a considerable margin its intended lifetime, which is absolutely wonderful for positional measurements, proper motion measurements, orbital binaries, and so on and so on and so on. And what has appeared so far is the third data release, DR3, which came out just over a year ago. And these are just some numbers. I've picked out a few of them. Distances and motions, 1.8 billion. So this would be representing something of order of 1% of our total galaxy population. Astrophysical parameters, by that I mean effective temperatures, surface gravities, and so on, something like 500 million. Radial velocities, 33 million, rotational velocities, 3 million, so on. These are numbers which dwarf any previous estimates. You know, something like Kepler, I think, generated something of order 30,000, 60,000 with K2 rotational velocities. Gaia, even with data release 3, just under 3 years of data, delivering something like 3 million. Huge numbers of variable stars, which are being classified through automatic processes, machine learning, and divided up into the different variability classes. Solar system objects, there's something like 160,000 asteroids that have been measured, and their orbits are being constructed from that. And there will be a lot more information on solar system objects coming out in future data releases. Even in terms of extragalactic objects, there are huge numbers of very uniform samples of quasar candidates, galaxy candidates. The Hipparcos catalogue had something around 30 stars in the Large Magellanic Cloud in the catalogue. There's something like 10 million in the Large Magellanic Cloud and around 1 million in the Small Magellanic Cloud. And from these, there's a lot of insights into the physical motions of these stars. So I'm going to switch to the second part of my talk, which is to just take you through some examples of the science that's coming out of this. Now, I think already Gaia is cited as being the ESA mission with the most number of scientific publications. What's the latest number? Do you know? 11,000. All right. All right. So if I fail to mention your favorite topic here, you will forgive me. But I want to give a flavor and just show you, again, it's not so much for the astrophysicists amongst us, but perhaps those coming from slightly different disciplines. What is it one is doing with all this information? Now, so I'm going to go quickly through a number of different topics. And if you fail to comprehend or you fail to understand what I've spoken about on one topic, it doesn't matter. We'll jump to the next one. But so first of all, the solar system, and of course our solar system, as illuminated by or compounded by the enormous advances that have been made in understanding exoplanet formation and so on, we now realize our solar system is a truly bizarrely complex, an enormously rich and complex system with not only the planets, the moons, but countless billions of smaller particles, asteroids and icy bodies, the comets. And the objective here is to understand a lot more about how the solar system formed, its detailed history again, which is proving to be very complex and very. But one of the things I wanted to point out then to start with is stellar occultations. Now, what is an occultation? As these rocky asteroids are moving through nearby space, and they happen to pass in front of another star, right? Fully by chance, a rocky body will pass in front of another star. And what happens is that rocky body will occult the light coming from the star, so the star intensity will drop off as the rocky body passes over it. And that contains actually quite a lot of information, for example, about the size of the asteroid. There are, I'll give some other examples in a moment, but the problem was before the existence of Gaia, these occultations were extremely difficult to predict. There were a handful of occultations predicted each year, and many of those would be wrong by several hours or even several thousand kilometers, meaning that if you set your telescope up in this location and expect to see an occultation, it will pass somewhere else because you haven't got the positional measurements of the star or the solar system body. The situation changed quite a bit with Hipparcos, and quite a few occultations became measurable, but the situation has been transformed with Gaia, and there are now thousands of these occultation events that are predicted, and there are large groups of, including amateur observers, which are using these predictions of the solar system body passing over a star to go out with their telescope, monitor the occultation, and then feed this information back to central bodies, which are then processing it to figure out, for example, the sizes of the bodies, in a number of cases, rings of debris around these. These are known in the case of Chariklo and Haumea, dwarf planet. And there's some lovely examples of, if a body has an atmosphere and that body passes across more or less the direct line of sight to the star, then what you see is the atmosphere acting like a lens and partway through the occultation, you see the focusing effect of the atmosphere. And here is an occultation of Triton. So it's one of the moons of Neptune. And there we see the occultation. And then halfway through the occultation, a big burst in intensity as the atmosphere of Triton is brought to focus by the occulting body. So there's a lot of information coming out on this. And one interesting area as well is the determination of angular diameters of stars through the diffraction signal at the edge of the occulting body. So that's first example. Second example, solar system flybys. There has been a long-standing idea that stars passing close to the sun disrupt the cometary bodies in the outer parts of the solar system. If they're disruptive, some of them will be deflected outwards, some of them will be deflected inwards. And there's quite a large body of literature which tries to look at the correlation between nearby passage of stars and extinction events on Earth due to this influence of a nearby body. I should say, I mentioned early on that space is enormous. You know, I gave you one analogy. Stars will never collide in our neighborhood. In our solar neighborhood, stars will never collide, but they can come close. And what some people are doing now is to look at all the stars in the solar neighborhood, trace their orbits over the last few million years, and to figure out which stars came close to the solar system in the distant past or the near future, and as a step along the way of figuring out whether these are correlated with mass extinction events. So this is some, excuse me, some work done by Corinne Baylor-Jones, in particular up at the Max Planck Institute, and he's identified hundreds of these star passages coming close to the sun. Switching topics, another area of interest is these interstellar travelers. So we know now that there are interstellar rocks that have been formed in other solar systems passing through our own solar system. We know that from their very extended hyperbolic orbits. And one of the things you want to do if you want to identify where these rocks came from is to propagate the positions of the sun backwards in time, but also the positions of the other stars backwards in time, and see whether the orbit of these rocks that are now passing through the solar system came from this body or that body. And again, there are a number of studies being done on that, trying to figure out this object Oumuamua, for example, which particular stellar system did it come from. On a related theme, solar siblings, was the sun born in isolation? Was it born as part of a cluster of stars? Most stars are born in clusters, so it would be rather surprising if the sun wasn't born in a cluster. But if the sun was born in a cluster, where are the other cluster members? So these are called solar siblings, objects which would have a similar age to the sun, a similar chemical composition to the sun. And again, a little bit like the stellar flybys, what people are doing is to propagate back, look at the stars in the solar neighborhood, propagate their orbits backwards in time, knowing the gravitational potential of the galaxy and so on, propagating the orbit of the sun backwards in time, and trying to see whether there are objects which started off with very similar space motions around the galaxy, but over, say, several hundred million years or whatever, have diverged in their position in space. So you're looking for objects which have got similar chemical composition, similar ages, and similar space velocities. And at least one of these has been announced. Solar sibling 1, it's a distance of about 1,000 light years. And these become interesting targets for searches for other planets or panspermia or ideas like that. I'm going to switch. That was a look at the local solar neighborhood. I'm going to look at what is Gaia telling us about solar structure and evolution. And there's really a lot of very elegant things coming out of there. And I will point to just two of them. One is the structure of the white dwarf sequence. So we're looking here at the Hertzsprung-Russell diagram, or more strictly a color magnitude diagram. So you're looking at the color of the star, which is related to the temperature of the star on the ordinate, and the absolute magnitude of the star on the on the abscissa, and the absolute magnitude of the star on the ordinate. And stars line up in this so-called Hertzsprung-Russell diagram according to where they are on this main sequence, the hydrogen burning sequence, later evolutionary phases, the giant branch, low mass stars which sit and consume their nuclear fuel for many times the age of the universe, and the white dwarfs, the endpoint of stellar evolution for the majority of low mass stars. Stars less than about 8 solar masses sit in these white dwarfs. And what one sees, I think, for the first time is the bimodal structure of the helium and hydrogen envelope white dwarfs, and more particular, this little feature that was identified in the first paper by Karin Babusio, a little band of stars which almost looks like a sort of an error in the data points, but they circulated this, and a white dwarf expert pointed out that 60 years ago there'd been a theoretical prediction that white dwarfs are actually crystallizing. So as they reach a certain temperature, the internal plasma starts solidifying and it forms a crystal lattice rather than a plasma, dense plasma. And what happens is that as it crystallizes, it gives out its latent heat of crystallization, so the same as any crystallizing substrate, and that delays the cooling of the white dwarf. So these things are cooling over many, many times the age of the universe, but this is one theoretical feature, one sort of theoretical property of the white dwarfs that had been predicted by Edwin Saltpeter and 2 Russians back in the 1960s, was observed for the first time in the Gaia Hertzsprung-Russell diagram and was attributed to white dwarf crystallization. And crystallization in white dwarfs now features in many, many papers in the astronomical literature. There's all kinds of interesting things that are going on. And I think before this, there was essentially nothing coming out on white dwarf crystallization. Our sun will become a white dwarf. Yes, that's this region here. I was going to talk a little bit about the discontinuity between the radiative and convection zone, but I will leave that and move on. So this is observational confirmation of crystallization, and theory predicts that this crystallization front is moving out at 1 or 2 centimeters per year. It delays cooling for 1 or 2 billions of years, and it's important for understanding. There are a number of other effects that come in there, trying to understand whether white dwarf cooling sequences are related to changes in the gravitational constant. Hypervelocity stars. So one of the things we see, you saw some of these stars when I showed this animation of stars in the solar neighborhood. Some are moving very, very rapidly, and they are moving rapidly for a number of different reasons. Some are moving through because they are stars from the halo, which are moving close to us. Others are stars which have escaped clusters through n-body encounters in the cluster. They're moving outwards at 100 kilometers per second compared to, say, 30 kilometers per second of a standard star in the solar neighborhood. These were identified for the first time about 60 or 70 years ago, but the realization about 20 years ago that there should be even higher velocity stars, these what so-called hypervelocity stars, and these are stars that were predicted to be moving through the galaxy at 1,000 kilometers per second or 2,000 kilometers per second, predicted in the late 1980s by Hills. The first of them was discovered from the SDS, the Sloan Digital Sky Survey, by Brown in 2005. And Hipparcos is identifying now quite a large number. I think we're up to something like 30 of these hypervelocity stars that are coming partly from the black hole in the center of the galaxy, but also through supernova, what do they call them, D6 events. So these are really sort of remarkable objects moving at very, very high velocities, creating bow shocks as they move through the galaxy halo. They will still take 300 million years to escape the galaxy, and there is some hope that they will be able to trace the dark matter content in the outer parts of the galaxy as a result of their physical motion. There's a number of very interesting things going on up at the Max Planck Institute for Astronomy. There's some very lovely papers coming out on galactic structure and so on, and discovery of black holes and things like that. But I wanted to pick this one out, which is, it may seem a little bit mundane, but I think it's really a sort of very exciting discovery in a way. The fact that binary stars appear to occur more frequently with the pairs of them of equal mass or equal magnitude or equal mass. All right, now this was first suggested back in the 1960s by Virginia Trimble as an observational problem, observing binary stars and measuring the delta magnitude between the binary components. And what Virginia Trimble found was that there were too many of them that were of equal magnitude. And this has remained an enigma, I think it's fair to say, more or less ever since. And there's been more and more work done on this over the years, but people are a little bit skeptical. But what you see in the data from EDR3 from Karen El-Badri and colleagues is these diagrams on the top right, which show what is the delta magnitude difference if the magnitudes of binary components were randomized. And then the bottom right is what is the real situation with binary stars in EDR3. And you can see that this strong band right the way through the center is binary star systems of equal mass, equal magnitude, whatever. And I think this is a really nice sort of observational confirmation. It only becomes apparent in very, very large numbers, in very, very uniform surveys. So it's seen, I would say, really convincingly for the first time in the EDR3 data. There are some nice ideas on why that should be so. You know, I could wave my hands and try and explain that, but I think this is going to say quite a lot about the formation of binary systems. This kind of information is going to say a lot about the formation and evolution of binary systems. So I'm going to switch to my penultimate topic, which is galaxy content and structure. And I think this is where Gaia is really, really blazing a trail in understanding what is going on in our galaxy. There were the first hints. I mean, people have known from theoretical work, people have had an understanding that you're going to see certain structures. You see the bar in the center of the galaxy, you see spiral arms, which originate from still contested physical processes. And there were certainly the first hints well, hints before Hipparcos, but certainly Hipparcos added the first sort of examples of a much richer dynamical structure in our solar neighborhood. And this has been now confirmed really in spades with Gaia. And we're seeing all sorts of very, very strong kinematic dynamic signatures in the space motions. And I'll try and give a couple of examples of those. So what we find now from these tens of millions or hundreds of millions of stars from the Gaia survey is a confirmation that there is indeed very, very rich structure going on in the galactic disk. The disk is deeply structured, strongly perturbed, and all sorts of things are flowing from this. Now, going back 20 years when I talked about the Hipparcos results, you start from the inside and go out. What is Hipparcos telling us about the solar neighborhood, and what can we then learn about the galaxy on a larger scale? I think today the interpretation of what's going on with Gaia is enormously facilitated by the kind of cosmological simulations that people are doing that are telling us about how structure arises in the universe, and as a result of that, what kind of structures might be existing in our own galaxy. So this is from the illustrious simulations of Volker Springel and colleagues. And you can just see there that you know, as a result of these models of dark matter and dark energy and feedback processes and star formation and so on, this is supposed to be something of the order of the size of our own galaxy. And this thing coming in from the side is something like the Large Magellanic Cloud. And it gives you hints about the kind of structure that you might be seeing today in our galaxy. So there's many things going on, which makes it, I think, very difficult to get a good conceptual picture of what is going on in our galaxy. But one of them, I'll start with tidal streams. So something like the 1990s, the first realization that the halo is being built up from gravitationally captured dwarf galaxies or minor members of our local group of galaxies. And in this little animation at the top right, you'll see the orange dot is supposed to be the center of our galaxy. And I've taken out every star in our galaxy and just left a captured galaxy, a small captured galaxy represented by a number of stars. And what you'll see as time goes on, as the gravitational field of our own galaxy captures the stars in the captured galaxy, these stars are spread out in space and they start mixing and disappearing into the overall structure of the halo. However, you can imagine that the angular momentum is still a key element in the properties of those stars. And people have started recognizing now these streams that are present in the galactic halo in very large numbers. There's something of order 20 or 30 of these streams now recognized. They've got very low metallicities typically, or similar metallicities as a result of the cannibalized galaxy. And they have in particular this property of the angular momentum, which allows them to be distinguished from the rest of the star population. So what we conclude from this is a rather clear picture that the galaxy halo has been built up from these cannibalized galaxies, and we're seeing them in great detail. I touch on two topics here, the Hercules stream on the left and the so-called Gaia phase space spiral on the right. Shall I try and explain those? If you look at stars, say, within a few hundred parsecs of the sun, it turns out that they are moving in very complex resonant motions because of the dynamical interaction with things like the galaxy bar at the center of our galaxy, or the spiral arms further out. And as you build up these very big samples with Gaia, you can go into this so-called phase space, this velocity structure as a function of velocity in the galaxy or position in the galaxy. And you can see all sorts of features in there, which again, if I simplify it in just a 30-second summary of this, are direct dynamical indicators that there is a bar, an extended bar sitting in the center of our galaxy. The phase space spiral on the right is something I think, again, a remarkable discovery, which if you look at the Z velocity, so the velocity of stars moving out of the galactic plane compared to the Z coordinate in the galactic plane, you see this sort of spiral structure which appears in there. And that is attributed to a perturber, a satellite galaxy, which has come close to our own galaxy 5 billion years ago, 10 billion years ago, 900 million years ago, consistent with the last pericentric passage of the Sagittarius dwarf galaxy. So we're starting to build up this very, very detailed picture. And a further point on the galaxy bar, and again, just to point out on the right-hand side there, is that there is evidence that this bar is decelerating, and it's decelerating by an amount which is consistent with the dragging of the dark matter halo. At least that is what this one paper claims. And I think there will be, we'll wait and see confirmatory papers on that. But to explain the motions of the stars in the solar neighborhood, you need to put in not only a resonant motion with respect to the bar, but a bar which is decelerating over cosmic time. And I think that's a wonderful discovery. Well, there's been some direct distance determination of the galactic center, but I'm going to just finish with one. I had some other examples there, but I'm running a little bit short in time. And just an example of galactic aberration. In the historical slide, I pointed out Bradley's determination in 1718 of the stellar aberration. This is the fact that the Earth, as the Earth moves around the sun, I'm the Earth and I'm moving around the sun, then starlight, which is coming in at the velocity c, is added to that, and you see the displacement of the star images as a result of that vectorial addition. The sun is also moving around the center of the galaxy. The sun moves around the center of the galaxy once every 250 million years, roughly. So it's gone around 40 times in the lifetime of the sun. And the sun's motion around the center of the galaxy is such that the vectorial direction of the sun moves by 4 microarcseconds per year. So because of the Earth's rotation around the center of the galaxy. Now, if that's the case, it should turn out that the positions of quasars, or rather the velocity of quasars, should reflect that motion. And this has been done in a paper by Sergei Kleiner in 2021, which fitted the dipole motion of the quasars, the proper motions of quasars, fitted just by this motion of the sun around the galaxy, and you end up with a very realistic number of about 5.05 plus or minus 0.35 microarcseconds per year. That just corresponds to the orbital period of the sun around the galaxy, which corresponds to an acceleration term of 2 times 10 to the minus 10 meters per second squared, compared to the acceleration of gravity on Earth of about 10 meters per second. And Joe Bowlby has described this as a revolutionary moment for galactic astrophysics. So I'm going to finish there. I've given you, I mean, I was asked to keep the talk to 50 minutes. I hope I haven't gone much beyond that. I tried to give you just a flavor of what Gaia is doing. Let me summarize by saying I'm not involved in Gaia. I haven't been for more than 10 years. It's a very large collaboration. More than 400 people are working on just producing the catalogs. So it's a huge, like many of these, space missions or big collaborative projects, it's a huge collaboration. It was launched in 2013. It's still operating today. It's the only project dedicated to determining distances, overall funding and management, of course, by the European Space Agency. I want to stress the immense capabilities of European industries. I think it's only when you see this kind of thing operating in a very, very hostile environment, operating more or less problem-free for 10 years, that you realize the tremendous technical capability that we have in Europe. We have that in the States, of course, and elsewhere, but we're talking about the European Space Agency and the European collaboration. It is a monumental piece of technical creativity. Operations as well is extremely complex. It's run by the operations team in Darmstadt. The global astrometric solution, these numbers are huge. If you try and get your head around, Uli and I were just comparing beforehand. The Hipparcos catalog occupied a shelf space of about 0.5 meter on our shelves. If you were to put the Gaia catalog in similar printed form, it would be roughly 10 kilometers of shelf space. These are huge numbers that describing 2 billion stars doesn't really quite do justice for. So 400 scientists and astronomers working with a huge amount of data, working against very, very tough schedules to get this out. And I think it's worth stressing as well that DR3, which came out last year, DR3 was based on 34 months of data. There are now 10 years of data. I happened to get hold of a 50-pound note. I don't have many of those, but there's a quote from Alan Turing at the bottom on the 50-pound note in the UK. This is only a foretaste of what's to come, and only a shadow of what is going to be. And I think we can say that with confidence, that DR4 at the end of 2025 and DR5 around 2030 are really going to be really transformational in understanding the galactic structure. I'm writing my own essays once a week on Gaia Scientific Results, which you can find there at my own website, which avoids me having to persuade other people to publish things and correct things and so on. And it just remains for me to say thank you very much for the invitation. Thank you very much for your attention.
Thank you so much, Michael. That was a fantastic insight and into a truly revolutionary undertaking. And I think we can all be proud to be here in Heidelberg, and also very privileged to hear your views on this. Thank you. I'm sure we have time maybe for a couple of questions from the hall. And I will start with Herr Jordan.
Michael, thank you very much for the nice talk. I would like to make a remark on the white dwarf cooling sequence. Shortly again, there is this bimodality that you showed, and you said the next one is more resolved. Yeah, there you see this bimodality of the two, interpreted as hydrogen-rich atmospheres and helium-rich atmosphere, which is actually not so true if you look in detail, because on the B part, you have as many hydrogen-rich ones as well. And just a few weeks ago now, two papers came out.
I saw the papers, I didn't read them yet.
Sorry, and this is really interpreted by unseen carbon in the atmosphere. A low amount of carbon shifts hydrogen atmosphere in this diagram to the sequence where the dBs are. And the amount is so low that you cannot see features from the carbon in that case. And interestingly, by two teams in parallel, that was discovered.
Thank you. I saw the papers. I haven't digested them, and I prepared this beforehand. But it's everything is moving very, very fast, you know. Thank you.
Yes, the beliefs are correct. But first, it was misinterpreted as something that if there are delays, then they actually have no. Sorry.
Normal white dwarfs have typically 0.6 solar masses, and so if they had 0.8 solar masses, the DA would lie on the dB sequence. However, this is not true. They all have basically the 0.6, but with carbon in the atmosphere, it shifted because the absorption shifts it, so to say, in the color and in the magnitude downwards.
And that is distinct from the question of the crystallization, though. But
A couple more questions.
Michael, thank you very much for an excellent summary of the history, but also of the results from Gaia. Talking a little bit more about the future, there's a lot of discussions about the infrared version of Gaia, and I'm very much interested in your scientific judgment. I mean, you are, of course, no longer project managers, so you're free to judge such a mission. Of course, I have my own opinion, but I would be interested to learn what you are thinking about it.
It's difficult a bit for me to answer or to know where to start. I think the moving into the infrared is certainly something which is extremely potentially very rich. I think one has to say that in terms of looking at the inner regions of the galaxy, you know, the obscured regions, and I think the indications are that if you can move to I mean, it's not very far into the infrared, it's 1.5 microns or something like this, then you will see a lot more stars. Now, I am not following Gaia Near, all right? And I'm purposely not following it because going from an idea to a reality is an awfully long and difficult journey. So I don't know what accuracies they're claiming. I think the next step in astrometry from space should be trying to figure out how to do a factor of 10 better in accuracy. If that could go hand in hand with the infrared, you know, this would be wonderful. But I think one shouldn't be embarking on a near infrared at the expense of accuracy, because if you can't get down to 100 microarc seconds, then you've got all these stars at the center of the galaxy that you don't know what they're doing anyway. So you have to have that hand in hand. And if you move a factor of 2 in wavelength, centroided wavelength, I don't know how you are going to maintain that accuracy. So unless we move to much, much lighter weight mirrors, you know, the problem is ESA has talked about NASA as well has talked about lightweight structures, free-flying interferometers. There's been a lot of talk of this, but we've never really seen real progress in that. So I think if one were to look at the next step in space astrometry, I would want to see a combination of accuracy and probably near infrared wavelengths.
So now it just remains for me to once again thank Michael Perryman. It's been a very remarkable listening to all this, and one can't help feeling that we're living in a very, very special epoch right now in the early 21st century. And we're very grateful to Michael for giving us such informative and deep insight to make us really feel that special. Thank you very much, Michael.